Good afternoon, everyone. My name is Wei Yu. It is my great pleasure to present our research work, PMP, a cost-effective force execution engine that features a probabilistic memory pre-planning method to allow crash-free execution. This is a joint work of Purdue University and the University of Virginia. Before introducing our work, let me give the research background. Malware is a prominent security threat, and exposing malware behavior is a critical task. However, malware behavior analysis faces some difficulties. A well-known difficulty is that the needed environment or setup may not be available, hence the malware cannot be executed. In addition, recent malware often makes use of time bomb and logic bomb that define very specific conditions to release payload. Some sophisticated malware even use cloaking techniques such as packing and VM or debugger detectors to prevent execution when the malware is being monitored. Researchers have proposed force execution, a dynamic analysis approach which allows to penetrate malware's self-protection mechanisms and various trigger conditions. It works by force-setting branch outcomes of some conditional instructions. As forcing execution paths could lead to corrupted states and hence exceptions, the biggest challenge of force execution is how to maintain execution crash-free. There is an existing work called X-Force that implements force execution for binary executables. This is a heavyweight solution that needs to check individual instructions, reason about pointer aliases on the fly, and repair invalid pointers by on-demand memory allocation. Such a solution not only entails substantial overhead, but also is difficult to implement correctly. To make force execution more practical, we propose a lightweight solution called PMP that does not require checking individual instructions. Rather does it require on-demand memory allocation and pointer repair. Instead, it achieves crash-free execution by pre-allocating a large memory buffer and then initializing the buffer and variables with carefully crafted values in a random fashion before the real execution. In this way, a force execution is very similar to a native one. We use the code snippet as an example to provide intuition about how X-Force and PMP work. This piece of code defines two variables, A and B. The variables will be initialized and accessed according to different conditions. Assume in execution, 9.5 takes the force branch, and hence the variable B is not allocated and initialized. Line 6 is forced to take the true branch. The program will crash at line 7 due to an invalid memory access on an initialized pointer variable B. X-Force checks all individual instructions and notes B is an invalid pointer variable when execution is forced to reach line 7. It then allocates a memory block for B and needs to update the pointer variable C since it has a alias relation with B arrow F2. Otherwise, 910 will not have a correct result. After allocating memory block and updating pointer aliases, the execution at line 7 will not crash. When performing force execution with PMP, a large memory buffer is pre-allocated, and the pointer variable B is initialized with a value that very likely points to a location within the pre-allocated memory area. And the pointer variable whose value is dereferenced from B arrow F2 also falls into the pre-allocated memory area. The execution at line 7 will not crash, and the pointer alias relationship between C and B arrow F2 is automatically established by the execution of line 7. Now we are going to introduce our work PMP. PMP consists of three components: the path explorer, the dispatcher, and executors. Given a target binary, the path explorer systematically generates a sequence of branch outcomes to enforce, including the pieces of the conditional instructions and their true or false values. We call it a path schema. PMP operates in rounds, each round executing a path schema. For each path schema, PMP further generates multiple versions of reliable initialization, each having different initial values. We call them memory schemas. A process is forked for each pass and memory schema and distributed to an executor for execution. At the end of each run, the dispatcher aggregates the results from the executors. Another pass schema is then computed by the pass explorer to get into the next run. The reason of having multiple memory schemas is to reduce the likelihood of coincidental address collisions. We go into details about the memory pre-planning. When a program is loaded, a pre-allocated memory area, or PAMA for short, is prepared by invoking the mmap system call to map a graphed file to the program address space. The file content is randomly generated in a way to minimize the chances for pointer pointing to unallocated space, which I will explain later. During execution, program variables, including global, local variables, and heap regions, are initialized by PMP with random 8 multiple values pointing to PAMA. Specifically, PMP intercepts the program entry point for initializing global variables, call instructions for initializing local variables, and memory allocations for initializing heap regions. Note that the PAMA preparation happens a priori and incurs negligible runtime overhead, while variable initialization occurs on the fly during execution. Both are generic and do not require the case-by-case crafting. We further discuss these steps. First, we discuss the PAMA preparation. PAMA is mapped at the lower part of the address space starting from 0. In order to accommodate null pointers or pointers with invalid small values. The word align addresses within PAMA are filled with carefully crafted random values. For a 64 kilobytes PAMA, the first two least significant bytes of a filling values are free to be set with a random 8 multiple values, because when such a value is interpreted as an address, it still falls within PAMA and will not cause invalid accesses. Other bytes are filled to 0. Note that such a value is essentially a valid word-aligned address in PAMA. In practice, we find that 4 megabytes of PAMA performs well. Now let's move on to the variable initialization. To initialize global variables, PMP reads the offset and size information of the .bss segment from the ELF header and sets the segment with random values indicating word-aligned PAMA addresses. To initialize the heap variables, PMP intercepts all memory allocations and sets the allocated regions to contain random word-aligned PAMA addresses. Initializing local variables is more complex. During program loading, PMP initializes the entire stack region like a heap region. The stack space may be overwritten as stack frames are pushed and popped frequently during execution. PMP intercepts each function invocation to initialize the overwritten stack regions. In the process of PAMA preparation and the variable initialization, the random filling values are carefully crafted to ensure they satisfy two critical properties as much as possible. The first property is self-contained memory behavior, or SCMB for short. That means if the filling value are interpreted as memory address, the corresponding access still fall into PAMA. Violations of SCMB lead to memory access exceptions. The second property is self-disambiguity memory behavior, or SDMB for short. That means it is highly unlikely that two semantically unrelated memory operations access the same random address. Violations of SDMB lead to Burger's dependencies and corrupted variable values. Let's revisit the example code to see how PMP ensures SCMB and SDMB properties. We still assume in an execution 9.5 takes the fourth branch and 9.6 takes the true branch. The variable B is not allocated and initialized. Although variable A is initialized by the original program code with an allocated heap region, the data in the heap region is not initialized. After the memory pre-planning, The pre-allocated memory area, the local stack, and the heap regions are filled with carefully crafted random values. Specifically, A is set to a dynamically allocated heap region at line 3, and B points to the adjacent 20 in Parma. Consider the read operation at line A that triggers a pointer dereference on A and yields the value 10, which is further interpreted as a JAS in the follow-up double dereference. Observe that any following dereferences will be within Parma and do not cause any exceptions. Let's illustrate the SCMB property. We also observe that the value of B arrow of F1 dereferenced at line 9 is different from that of B arrow F2 dereferenced at line 7, and hence this disambiguate themselves, which illustrates SDMB. PMP is implemented based on the QMU user mode emulator. Specifically, PMP instruments conditional jumps and indirect jumps to enforce path schema. Currently, PMP supports ERF binary on the x86 64-bit platform. It can be extended to support other architectures due to the cross-platform feature of QMU. We leave it as our future work. To make PMP applicable to real-world executables, we take great efforts to solve some practical challenges. We will not go into details due to time limitation. Discussions will be found in our paper. Now we perform probability analysis on the soundness of PMP. To facilitate discussion, we introduce the following definitions. With these definitions, we study the probability guarantee of PMP for the SCMB and SDMB properties. Specifically, we consider 3 types of errors. The first type of error is out-of-bound access, whose probability is calculated by equation 1. The second type of error is coincidental adjacent collision, whose probability is calculated by equation 2. The third type of error is coincidental adjacent overlap, whose probability is calculated by equation 3. The detailed proof can be found in our paper. In a typical setting, PMP is configured to have a 4 MB pre-allocated memory area and 2 executors. The diversity of filling values is set to be 1, and parameters alpha, beta, gamma are also set to the typical values. In such a setting, the probability of error 1 and error 2 are negligibly small, and the probability of error 3 is still reasonably low. We evaluate PMP with the SPEC 2000 benchmark set as well as a set of malware samples on a desktop computer. We run SPEC 2000 without time limit and set 5 minutes timeout for each malware sample. The first set of experiments is to evaluate PMP with the SPEC 2000 benchmark set. SPEC 2000 contains 12 real-world programs. Some of them are large, such as GCC. We choose SPEC 2000 for the purpose of comparison as it was used in X-Force. The comparison is performed on different aspects. The evaluation results show that PMP is 84 times faster than X-Force with a similar failure rate. PMP has compatible code coverage with X-Force, which is around 83% on average. For some programs, PMP achieves 100% code coverage, while X-Force does not. We also checked the detection results of memory dependence and found that X-Force has 6.5 times more false positive and 10% times more false negatives than PMP. The second set of experiments is to evaluate PMP with the real-world malware samples. We use 400 malware samples. Half of them are acquired from VirusTotal, and the other half fall into the set of malware used in the Pandora project. We compare the malware analysis result of PMP with that of other malware analysis tools, including Pandora, Harbor, Cuckoo, as well as X-Force. Besides, we implemented 2 popular anti-evasion methods, that is, system time fast-forwarding and anti-virtualization detection, as extensions to Cuckoo. We named the extended system Cuckoo++. The comparison is performed on different aspects. The figures on this slide show the overall result. On average, PMP is 9.8 times faster than X-Force and yields past skimmers with 1.5 times longer than X-Force. We use a case study on a real-world sniffer malware sample to illustrate the advantage of PMP. The sniffer is equipped with a VM detection-based cloaking technique. The code snippet in this slide shows a simplified version of its main processing logic. If a VM environment is detected, the malware sample deletes itself and exists. Otherwise, it enters a sniffing loop, which randomly selects an internet IP address and a known vulnerability and checks whether the host or with the IP contains the vulnerability. If so, the information about the vulnerable host is sent to the server, and the payload is sent to the vulnerable host. The comparison of different tools on this malware is shown in this table. As we can see, PMP exposes the most behavior. Further manual inspection shows that Cuckoo and Harbor cannot expose the aforementioned behaviors. Cuckoo++ and Pandora can expose the network communication to the selected IP address, since they are enhanced to conceive VM-generated artifacts. However, they cannot expose standing vulnerable host information and payload, since the analysis environment is often offline, and there may not exist a vulnerable host on the internet. X-Force can expose both in theory, but fails within the timeout limit due to its substantially larger runtime overhead. PMP can expose both behaviors. The experimental version of PMP is now available on the GitHub. Welcome to download and try it. This is the end of my presentation. Thanks for your time, and I'm happy to take any questions.